We're going to look at review problems for the final exam. Again, these come from all sorts of different sources that you guys selected. So the first question is going to be on equilibrium, specifically solubility. Number 9 on Quest. And then we'll look at Halflife, the Chatelier's principle, fission versus fusion, a question from the multiple choice review about which condition will 0.5 moles of sample occupy when it has 11.2 liters, and then polar versus non-polar. So the first question is from UT Quest. This is one version of it. Again, yours might be slightly different, but it'll use the same idea. KSP is a special type of equilibrium, and the SP stands for solubility product. I call it special K because it is the one, it's not only a breakfast cereal, but it is the one equilibrium situation where you use a special trick. And all this trick is using the ratio of how something dissolves. So this substance, calcium hydroxide, whenever you have a KSP problem, that means that it is a solid dissolving into its ions. So the first thing to do is to write the equation for how the substance dissolves. Now, if you look at this equation, is this equation balanced as written right now? No, not balanced. I have to add a 2 in front of the OH because there are 2 parts of hydroxide for every 1 part of calcium. So this is a little bit of a tricky problem because of that 2 right there. So the first thing we write is the equation. The next thing we can write down is the K expression. And you guys know the rules on this. It's what over what for K? Products over reactants. Now the products are both aqueous. They're dissolved in water. Okay, and you don't have to write aqueous, but if you remember, it is. And so I write the first product, which is calcium ions, concentration of those, times the second product, which is hydroxide ions. And there is a 2 here, so it has to be squared due to the law of mass action. Now, if you wrote it just with K, that's fine. If you put an SP there, that's the technical term chemists use for that equilibrium. Why didn't I write calcium hydroxide on the bottom? It's 1. It's a solid. So you don't have to write it, or you can write it, your choice, as a 1. If you write it as calcium hydroxide, that's not going to work. So this is our KXP expression. Now, the problem with this is we're trying to find KSP, and we're only given the molar solubility. Now, molar solubility, when calcium hydroxide is placed into water, some of it dissolves. Does all of it dissolve? No, because it's at equilibrium. Some of it does. We don't know what that sum is. So they call that its solubility. So if some of this dissolves, let's call it S for sum or solubility. If some of it dissolves, I don't know how much it is, that's why I wrote S, then how much calcium ions would be in solution? They only come from the calcium hydroxide. So if I have some here, I'm going to have some here. Now, why is it just the same variable? Because it's a 1-to-1 ratio. For every 1 calcium hydroxide that breaks up, you get 1 calcium. However, if I look at the OH, how many OHs do you get for every 1 calcium that breaks apart? Not 1, but 2. So this is going to be sum times 2. All right? So it's going to be double the amount of calcium in this solution. So if we have this as calcium, and there's 2 hydroxides attached to it like this, it breaks apart, you get a calcium, and you get 2 hydroxides floating around. Okay? And that's a 2 plus and minus and so on and so forth. So there's the ratio. Now once you know the ratio, the cool thing is the solubility is called the molar solubility, and that's equal to S. So what you do is you plug in your variable S into the equation. So your KSP equals S, the concentration of S, times OH. Now OH is the tricky part. OH is 2S. And the whole quantity is squared. 2S is squared. You can't forget that because that's the law of mass action. Here's where the math trickiness can come in. If the exponents are 2, 3, 4, or something like that, you have to watch out for this. So I'm going to do it the very simple math way, which is I'm going to write it all out and then multiply it so I don't mess up. Just some of you probably could do that in your head. So S times S times S equals S cubed. 2 times 2 equals 4. That equals our KSP. And now our S is this variable. We plug that in here for the S. So it's 4 times 0.011 moles per liter cubed. And that equals our KSP. So I type 0.011 and I cube it, and then I multiply it by 4. That's how my calculator works. If yours does it the opposite way, you can plug it in there, and that will give you your KSP answer. And for this particular one, I believe this one had an answer of 5.3 times 10 to the negative 6th. And K is the one thing that doesn't have units, so that's why there's no units on this. So 0.011 cubed times 4, and then in scientific notation I got 5.324 times 10 to the negative 6, so that's, I think it was a multiple choice there. That's the answer. Now the reason I call this tricky is because of the mole ratio, and I only use this mole ratio in KSP problems. Okay, the mole ratio plays a role in other chemistry, but if this was a gas here, or this was aqueous and these were both aqueous, the ratio would not be that 2-to-1 exact ratio. It would be close, but it would not be exact. So that's the trick that works for solubility only. If you have a normal KSP, don't do this trick. It'll probably give you the wrong answer, like 100% of the time. So that's the trick on that one. All right, next problem here is asking about half-life. Okay, so half-life, there are different ways of determining the amount of sample left using half-life. The way I like to do it, the easiest way, which requires the least amount of equation memorizing, is you start with a certain amount of sample. Let's say you had 100 grams of the sample. The half-life is the amount of time for half the sample to decay, especially if it's a radioactive half-life. So this sample here will have a certain amount of time, called the half-life, T1/2, for it to decay. Now, I don't know what the sample is. The half-life depends on how radioactive and how stable the nucleus is. But if the half-life was 10 years, for example, after 10 years, half of this original element would be decomposed, and there would only be half left. So 100 to 50 grams. Okay. Now, different half-life problems might ask how much is left after 100 years. Okay. So if you have this information, the half-life is 10 years, you have this information and this information, 10 years and 100 grams, that's all they'll give you. So the way I can do this without a lot of equations, so you start with 100 and you go, okay, there's 100 years and there's 10 years per half-life. So that's how many half-lives? 10 half-lives passed. So all I do is I go, okay, I started with 100 grams. I'm going to divide it by 2. How many times am I going to divide it by 2? 10 times, right? So divide it by 2 10 times. Some people like the little math saying 100 grams divided by 2 10 times. That's the math there. And that tells us the amount left in grams. Or you can just do your calculator 10 times. 100 divided by 2 divided by 2 divided by 2 divided by 2. Okay, or you can do it in your head if you're extremely skilled in math. Once I get past a certain point, I can't do the decimals anymore. But that's how to write the answer. So if I do this in my calculator, 100 divided by 2 to the 10th. So 100 divided by 1024, I think. So it looks like this has about 0.0977 grams left at the end. All right. Is that good for Half-Life, or is there something else you want to know about Half-Life? Yes, sir.
After like 15 years.
Yep.
How many Half-Life would it take to get like 20 of that substance left?
Okay. So that means you'd be working kind of backwards to try to figure out how many half-lives. So what you can do on that here is this is the amount left. This is the original amount. Okay. So if you have the amount left and the original amount, I think your only variable would be that, right? So that would be a way of solving it. What I would do is I'd take the original amount and I'd start dividing by 2. Count how many times I divided by 2. There is an equation for doing this as well when you have more advanced cases, but I think all the ones we have on UT Quest should be able to solve that. I tried not to use the equation version on the Half-Life problems. All right, next one here is Le Chatelier's principle. So this is affectionately known as LCP. All right, so Le Chatelier's principle, we always need an equation for this. So here is one equation of a reaction between hydrogen and bromine to make HBr. These are all gases. If there was any solids in there, they would not affect equilibrium. So if you add or remove solids, they don't change equilibrium. That's often a question asked, solids and liquids. So in this case, they're all gases. We can solve for what happens when you add or remove a chemical. So the way it works with Le Chatelier's principle is if you add a substance, like we added bromine gas to this container that contained all these gases, what happens is when you add more bromines, there's more bromines to collide with the hydrogens. So that extra amount of bromines can react with the hydrogens. Why does it react with the hydrogen? Well, when you have more bromines, you have a higher concentration. There's going to be more collisions, more reactions, and that will make more HBr. So this shifts the equilibrium towards the HBr. More of that will be made. Now, if this was an exothermic reaction, the heat would be on the product side. You would have to be told that information. And it could be written as heat or like 67 kilojoules. Again, that's not necessarily the heat of this reaction, but it could be written either way. When you add bromine to this system, and only bromine, it increases the HBr. It also increases the heat because this arrow is pointing towards the products. The hydrogen, though, has reacted with the bromine, so its concentration goes down because it reacted with the bromine. So this would explain what happens when you add bromine to the situation. The other thing you could do is if you reduce the temperature. If you reduce the temperature, what does that decrease in this equation? So reducing the temperature lowers the what? The heat. So reducing the temperature is like removing heat. Okay? So if you remove a substance, the equilibrium shifts towards the removal. So if I took out heat, what happens is as you take out the heat, the equilibrium shifts towards trying to make more heat. To do that, it has to make more products. So it increases the concentration of the HBr, decreases the bromine, and decreases the hydrogen. So it tries to shift to negate the change that you did. So if you adjust something at equilibrium, it's trying to go back to rebalance that equilibrium situation. Okay? And so each of these is based on that principle. Reducing a chemical does the same thing. If you remove this chemical, for example, it shifts towards the removal. That goes down, and the heat would probably actually go up in this case. If you only removed HBr. The other thing you can change is the pressure. And oftentimes they will ask this from volume's point of view. Okay? Not always, but remember that pressure and volume are inversely related if they ask about that. For this case, if we change the pressure, let's say we increase the pressure, how would this change the equilibrium? What you need to do for pressure changes is if you increase the pressure of the whole system, you count how many moles are on the left. There's 2 moles on the left. There's 2 moles on the right. When you increase the pressure, you need to go to the side with the smaller number of moles. In this case, which one has the smaller number of moles? 2 and 2, are they? Is there anyone that's smaller? No, so they're equal. So when you increase the pressure, it doesn't change anything. So that, you would have to have numbers here. So increase the pressure normally always goes to the side with the smaller number of moles. And remember, we only count the coefficients for the moles in the Chatelier's principle. And again, if we decrease the pressure, it would be the opposite. And this is the pressure of the entire system. So in this problem, they might ask, well, what happens if I increase the pressure of the HBr? If you increase just the pressure of the HBr, that's adding HBr. It's going to shift away from the addition and increase the Br and the H2. So if you say increase the pressure of just the HBr, that's like adding a chemical. So if you added this chemical, it would shift away. The heat would actually go down in this case if you added the chemical. So Le Chatelier's principle predicts what happens when you change one thing in the reaction. All right. Any other questions on Le Chatelier's principle you have? Or clarifications? Yeah. No, not necessarily. This equation happens to have 2 moles on the left and 2 on the right. If you had an equation like this, nitrogen combining with hydrogen to make NH3, for example. If you look at this one here, if it's exothermic, you have 1 plus 3, you have 4 moles on the left and only 2 moles on the right. So they could have the same, but oftentimes they don't, especially if they're asking, if you increase the pressure, what happens? But it's either it shifts to the right, shifts to the left, or has no change. And it's the gases in aqueous that, well, with pressure, it's usually gases. Gases affect the equilibrium. All right. All right, the next question I saw was fission versus fusion. All right, fission versus fusion. This is from nuclear chemistry. A fission reaction is when you have one thing breaking up into 2 smaller things. Okay? Usually nuclear fission is when one isotope breaks into 2 daughter isotopes. Okay? Now, it's very, very similar to nuclear decay. I almost think about it as the same thing, but it is only different in the fact that these daughter isotopes are usually more massive. In alpha decay, you have an alpha particle, which is a helium nucleus, and then this is called your parent isotope and your daughter isotope. And remember, the mass numbers have to be equal on each side, and the atomic numbers have to be equal for a balanced nuclear equation. In nuclear fusion, you take an element and fuse it with another element to produce a new element. So two smaller elements coming together to make a new element. Both of these reactions often produce energy as a product. The amount of energy compared to chemical reactions is 10 to the 9th magnitude, so it's much greater. And the reason why is this is happening at the atomic level. There's a lot more reactions happening. So each atomic reaction that happens releases a small amount of energy. But when you multiply that by 6.02 times 10 to the 23rd, that releases a ton of energy comparatively. And so that's why there's so much energy released in nuclear fission or nuclear fusion. Nuclear fusion happens on the sun. Okay, nuclear fission, that has happened in nuclear power plants. And this also can be used for nuclear weapons. It is a different reaction, so it's not exactly the same. The reaction is different, and the way it's controlled is different. You can make a parent less stable by adding a neutron. And that's one way that nuclear fission can be controlled. You add neutrons, and then when you want it to stop, you take away the neutrons, and the reaction stops. Yeah.
So fission isn't a natural process. It doesn't happen anywhere in the universe.
Actually, it does happen. It does happen naturally as well. There are two places that it's known to happen. Well, there's one place it's known to happen and one place it's hypothesized. There was a place where they found all the products, so all the daughters of nuclear fusion. So they found some uranium and all the possible isotopes that it changes into. And what happened was the uranium was separated by the neutron generators, and it was separated by cracks in the rocks. And what would happen is when it would rain, water would fill this up, and then the neutrons were able to pass over into the uranium. And the uranium would go through nuclear fission, and they have all of the products. So most people don't think it happens in nature, but it was discovered, I can't remember how long ago, that there are all the products of nuclear fission, and it's believed that that's what caused the reaction to occur. It's also believed possibly that the core of the Earth is made of iron that's liquid. That's what we believe, at least. And at first they thought it was gravity that caused it to be liquid, but gravity may not have enough force to cause it to liquefy. More likely, it's nuclear reactions that are happening inside of our planet that are producing this large amount of heat. And so there's some natural cases where it happens. It's just harder to discover. Yeah. So we thought we invented it, but nope, we didn't. Yeah.
So both of these reactions release energy, right?
Yes. Uh-huh.
How is that possible?
How is it possible? Well, what happens is the way they release energy is as the particles come together or the particles break apart, there is a change in mass, and that small change in mass, it's called mass defect, times the speed of light squared gives us what's called the binding energy. So when you rearrange the nucleus, you're changing the mass slightly. And as that mass is changing, it releases energy.
Wait, so some of the mass becomes energy?
Correct. And this is predicted by this equation, which is Einstein's equation. And that's what's pretty amazing about nuclear chemistry. is the fact we can predict, if I do put these two together, how much energy will it produce? If I take these two. Now, in this case here, you're adding neutrons to it, and you're actually breaking it apart, and more neutrons are produced. In this one here, in this case, it looks very clean, like two things coming together, but the mass of the nuclear particles does change a very small amount, and that's what releases the energy.
While I was reading Quest, while I was googling some of the stuff from Quest,
Yeah.
like the concepts and stuff, it said that fission, after it reaches a certain point, it absorbs energy. It's endothermic.
That is definitely true. It gets to a certain point, and that's why we use uranium often in nuclear power plants, is that releases energy, but as the daughter isotopes keep forming, those go through natural processes, or if they're hit by neutrons, they become more stable, or less stable, I'm sorry. But as you keep going, it breaks into smaller and smaller pieces. It goes more and more towards iron, and iron has a unique amount of stability where it keeps going towards that point. So one of the things that scientists are still looking into is why is it that things, small things, fuse together to make bigger things up to iron, and big things break down until they make iron. And so there's a seems that's what the data suggests, and we don't know why yet. And there are some things that are more stable than others, and they actually call it magic numbers based on stability. They say certain ratios are more stable. I think it's even numbers are more stable than odd. So why is that is still a question. That there's statistical relationships for fusion versus fission. All right, let's look at the next one here. Let's see what we have here. Shotley's principle. All right, so this one here is from the multiple choice review. It says, what condition will 0.5 mole sample occupy at 11.2 liters? All right, so if you look at this here, if you take 11.2 liters and you divide it by 0.50 moles, okay, this gives us a special ratio of 11.2 divided by 0.50. This gives us the ratio of 22.4 liters in 1 mole. Okay. Now this ratio is a special ratio because it's called the molar volume. And 1 mole of a gas will always equal 22.4 liters at STP. So there's only one set of conditions at which this will be true: standard, temperature, and pressure. So on the multiple choice review, it's basically asking what is STP. Although if you didn't know this was molar volume, that's the trick on that one. So standard temperature is 0 degrees Celsius, which is equal to 273 Kelvin. And this is also the freezing point of water. So if you have ice water, it's going to be at that temperature. Standard pressure is equal to 1 atmosphere, which is equal to sea level. So the way I remember STP is STP stands for surf the pipe. Now I know some people say STP stands for other things that we don't do in chemistry, or you should not do. But surf the pipe is how I remember it. And the reason I remember that is when I was younger, I used to actually surf the pipe, and now I'm old, I just sit on the side and watch other people surf. As I sit on the side and watch other people surf, usually, although I do like going out every once in a while, it's nice, I have a nice big cooler filled with ice cold soda. So I've got my ice cold soda in the cooler. Here I am. I'm really bad at drawing. There we go. I'm sitting down. Yay! There we go. Here's my surfboard sitting on the side. There we go. And here's a wave. There we go. And there we go. And there's the really cool surfer dude. Woo! Yeah. There's your hair. Woo! Surfing. All right. So that person's surfing the pipe. I'm reaching in and grabbing an ice cold soda, which happens to be at 0 degrees Celsius. And there is 1 atmosphere of air above my head. That is called 1 ATM. That is standard pressure. So STP is the condition that 0.5 moles will occupy 11.2 liters. Yes, sir.
When it says STP, would you ever use Celsius, or do you just go to Kelvin?
If I had STP, usually you're using Kelvin in a problem, but if you have STP, you can also use this molar volume in a problem. That usually solves the problem faster. So if you know STP, you can use PIBNERT, or you can use molar volume, depending on what they're asking. So if you had 10 moles of a gas at STP, I got 10 moles at STP, and it wants to know the liters. That's going to be, there's 1 mole, 22.4. There's my ratio. So the liters would be 224 liters. So that's one way of using it. It's kind of like a shortcut in chemistry. So on the on the review, they like to know, do you know what STP is? I'm not sure why it's so important, because you can look it up, but for some reason they want you to memorize that. Or they give it to you. I can't remember what the equation sheet says. I'm not going to look on the green equation sheet. They might give it to you now. But that particular test question was asking for it. All right. All right, next one is polar versus nonpolar. Polar versus nonpolar includes a lot of chemical concepts that we've learned. There are 2 things to always consider in polar versus nonpolar molecules. The first thing is the electronegativity difference, and the second thing is the shape. Okay? So, electronegativity difference is between 2 atoms. The one that is closer to fluorine is a greater electronegativity, and that would be slightly negative. The other one is going to be slightly positive. Now, when you only have two atoms, it makes it easy. Okay? Number 1, that will determine the polarity. The second thing is when you have something with more than 2 atoms, you have to look at the shape. So the main shapes we have, we've got a tetrahedral shape. We have a linear shape, which is when we have only 2 electron domains. And we also have a trigonal planar shape. And that's where we have 3 electron domains and exactly 120 degrees between each. This is 180. And the angle here for the tetrahedron is 109.5 degrees. For polarity, if you have something that is different elements, it will usually be polar. So different elements makes it polar, except if the dipoles cancel. So in a tetrahedral shape, if everything around the central atom is the same, if it's symmetrical, then it can be nonpolar. If it's asymmetrical, which means not symmetrical, okay, it will be polar. How do I know that? Well, if it's not the same, it's going to be polar. If it is the same and it has a symmetrical shape, these are the 3 symmetrical shapes here, then it will be nonpolar. Now, you know there's other shapes, bent and pyramidal. The good thing about these shapes is they are not symmetrical, they are asymmetrical, so they're always polar. It doesn't matter what elements you have. Okay, so you don't have to think about those too much. As long as they don't have, well, yeah, they cannot be nonpolar, which is nice. So electronegativity difference is usually the bond polarity, and then the shape of the molecule for whether it's the few cases where it's nonpolar. And remember, tetrahedral is our basic shape. We remove an element and add a lone pair, we get pyramidal. Take away another one, we get bent. 2 electron domains is linear, so this is 4 electron domains, 2 electron domains, and 3 electron domains. And that's all the electron domains we cover in regular chemistry. There are other cases where we have, like we had with our cobalt demonstration, where we had 6 waters attached to it, but that is not something we cover in regular chemistry. The other thing about polar versus nonpolar is we know polar and nonpolar, do they mix? No, they do not mix. So they are insoluble in one another, okay, most of the time. And that has to do with the intermolecular forces. So something that's polar will have a stronger intermolecular force with something else that's polar. With something that's nonpolar, it's less of an attraction, and that's why they're said to be insoluble or not dissolving in one another very easily. So those are the questions for today.